Achha. So, therefore, we had already discussed, if you remember, we had discussed the PV diagram and the TV diagrams already. The only thing which was left was a PT diagram. Again, we start with the same thing. Suppose we have pressure versus temperature. Again, we start with benzene at very low temperatures, it was 1, and then we keep on heating it at constant pressure, it comes to some particular point, and then there is change of phase. Since the change of phase occurs under isobaric isothermal conditions, so therefore 2 and 3 they coincide here. Then again it starts to heat, it heats till a quite till the liquid changes to the vapor phase. Again phases 4 and 5, if you recollect, the transition from liquid to vapor, that occurs at a particular point in this particular case, and then the vapor continues to be heated. In this particular way, we can keep on drawing these particular curves for different substance for different specific volumes. We can keep on drawing these particular curves, and as we go for higher and higher volumes, higher and higher pressures, we find that these particular curves are there, just the location of these saturation curves are different. Again we join the different saturation points to give us saturation curves, and under that case what do we get? We get something of this sort. This is going to be this, I could not draw them well, this, and then this is going to be something of this sort, right. So, we find that we have a solid vapor transition curve, which is nothing but the sublimation curve. Okay. Now, below this sublimation curve we have a solid here, and then we have a liquid vapor. This is known as the vaporization curve. It separates this is the solid zone, this is the liquid zone, this is the vapor zone. So, it separates the liquid and the vapor, and we also have a fusion curve which marks the transition from the solid and liquid. Again, I would like to remind you that the fusion curve, it can continue indefinitely, as I have said, but this particular curve, it has to terminate at point C, which is given by PC TC. So, therefore, this terminates here, this does not terminate, and the sublimation curve also terminates. All these three they terminate at the triple point, which reduces to a point here, since this triple point is marked by a particular T triple point and P triple point, right. Here I would also like to mention one more thing which will be evident from this particular graph. We find out that more or less the slopes of sublimation curves and vaporization curves are always positive. The slope for sublimation curve is steeper as compared to the vaporization curve, and usually the slope of the fusion curve is also positive. It is negative only for certain substances. For example, the most common substance that we come across, which is water. Now, why all these things happen? You need to remember that water contracts on freezing, but exactly why it happens and all the characteristics of the PT curves, that we will be dealing after a few more classes, where we will be dealing with equations like Clausius-Clapeyron equation. All of these are going to predict the slopes of these PT curves and also the reasons for number of things that we observe in this particular case. Now, by this time you must have realized that this particular point, the critical point here and the critical points which I have shown here, these critical points, they are constants characterizing the substance, just like triple points, right. So, therefore, for every substance, if you want some very reliable property, then definitely you would like to locate the critical point. Now, as it is quite evident that it is easier to measure pressure temperature as compared to volume. So, mostly what we do, we measure the critical pressure temperature and then try to predict the critical molar volume from these things, right. So, therefore, in order to determine this, there is a very popular experiment which I will be mentioning in very brief, which is known as the disappearing meniscus experiment. In this experiment, this is a very common experiment which you perform in the chemistry laboratory. Usually, this is performed with SF6, since if its critical point is near about 45.5 degrees centigrade or something. So, therefore, it is easy to perform the experiment. What do you have? You have a closed seal tube. Now, when you have a closed seal tube, what does it mean? And then here you introduce some portion of the liquid that you whose critical point you want to measure. Usually the experiments, as I have said, they are performed with SF6, right. Now, what happens in this particular system, more or less you have introduced some amount of liquid. So, therefore, the mass remains constant, and then since it is sealed from all ends, so its total volume also remains constant, right. So, therefore, what does it imply? It implies that the molar volume of the liquid, that also remains constant, fine. Now, under this condition, if you start heating the tube, what do you expect is going to happen? Quite naturally, just suddenly offbeat, you would like to say that moment we start heating the tube, the liquid starts vaporizing and more vapor will be formed, and then at one point the entire tube will be filled with the vapor. Now, this will not always happen. It will depend upon the molar volume with which we have started. For example, if I refer to the previous figure, it is going to be evident to you. Suppose I refer to the previous figure, then in this particular case it appears to you. Yeah, if you just observe this figure, it all depends on from where you have started the experiments. Suppose your molar volume was somewhere here, sorry, very sorry. Suppose your molar volume was say somewhere here. From here you start heating it. What are you basically doing? You have kept the molar volume constant and you are increasing its temperature, fine. So, therefore, you keep on heating, what happens? You find that you are shifting actually towards higher quality lines. If you draw quality lines here, you are shifting towards higher quality lines till you reach the quality line x equals to 1, which is nothing but the saturated vapor curve, and when you have reached this curve, you find that your meniscus, it keeps on decreasing till at one point it disappears and the whole thing is filled up with the vapor phase, and you have entered the your superheated vapor region, fine. Suppose you are starting with a very low molar volume, or with a very low molar volume you have started. For example, say for instance, you have started from somewhere here, right. Now, you keep on heating it. What are you doing basically? Just notice, again you are following a vertical line. What are you doing here? You are going from a higher quality line to a lower quality line, and then you keep on shifting quality lines till you reach x equals to 0, the saturated liquid curve, and then if you continue the heating, you have actually entered into the subcooled liquid region. So, in this particular case, what happens? You find that your liquid meniscus, it keeps on going up, and this continues till finally the whole thing becomes filled up with the liquid. Now, suppose you start the experiments with some particular volume of the molar volume of the mixture, such that the molar volume, it corresponds to the critical point. Now, if you start heating it, what will you expect? You are going vertically in the same way. Please note that you are following a constant quality line in this particular case. You keep on following this constant quality line and continue the heating. You will find that no matter how much you heat, your line is going, your meniscus will be remaining fixed at one particular location. It neither rises nor it falls, it simply remains constant in this particular portion, and this thing it continues till you are reaching the critical point. Moment you have reached the critical point, the meniscus suddenly disappears, and you know that this is the condition of, this is the critical condition. At that particular condition, if you measure the temperature and the pressure, you are able to locate TC and PC. You can keep on performing the experiments, you will find that the meniscus disappears, comes back, means you are just operating at this particular point. You just increase the heat, again decrease the heat, just decrease the heat, again increase the heat. If you keep on continuing this, you will find that the meniscus keeps on coming and going, but it remains at one particular location, and this corresponds to your TC and PC. So, by this way, this is a very easy way of finding out the critical temperature. And once you have found out the critical temperature, then from the critical temperature, it's much easier to find out the critical volume. Just I'll show you what exactly happens. Suppose this is the critical temperature and suppose this is rho, or in other words we can also plot the volume also in this particular case. Exactly what are we doing here? So therefore, or in other we plot rho versus T, that is going to be easier. So what do we do? Suppose for the liquid we are plotting the orthobaric densities, which means the densities along the liquid vapor coexistence curve. What do we find? As we keep on heating, the liquid density keeps on decreasing, right? The liquid density, this is rho liquid, it keeps on decreasing because the liquid expands and it also vaporizes at the same time. What happens to the vapor? Much amount of vapor is being added, and also we find that the vapor it expands. So, we find that the liquid density keeps on decreasing, the vapor density keeps on increasing till at T equals to Tc, both the densities they become identical, right. So, therefore, here also we find that if we would be plotting the rho bar, which is nothing but rho liquid plus rho vapor by 2. If we are plotting this versus temperature, then we find usually this is the slope of this particular curve, and this particular curve it is usually linear in nature, and the slope it can be obtained as rho bar equals to A plus Bt, right. So, from here you can find out A and you can find out B, and then you can find out rho bar at T equals to Tc. So, this is a standard way of finding out T equals to Tc or the critical conditions for pure component substances. So, apart from this, I would like to say these are the basic phase diagrams, but the phase diagrams which we use mostly for our purposes, as you already know, that those phase diagrams are primarily, apart from these phase diagrams, they are primarily the temperature entropy, and more common is the enthalpy entropy diagram, which is commonly known as the Moliere chart. The importance of Moliere chart is, the first thing is it can be plotted on an elongated scale, and here if you observe, you find that we have the isobaric lines and we have these are the isobaric lines, we have these are the isothermal lines, and we have lines of the constant quality lines. So, therefore, this particular curve it is complete in all respects, and if we know the pressure, the temperature if we know the pressure and temperature of the different points, and then we are in a position to find out its enthalpy, to find out its entropy, and if suppose the conditions are such that it lies within this two phase dome, then in that case we can also find out the dryness fraction or the quality of the mixture. So, therefore, usually we find that the Moliere diagrams are the diagrams which we use most frequently in order to find out the properties, measurable as well as non-measurable, of pure component substances in the liquid phase, mostly in the liquid phase, vapor phase, as well as in the liquid vapor region. Now, this was all about the graphical representations of PVT behaviors. Apart from this, naturally, as I have already mentioned, we need to have some equations. When I tell you about the equations, the first equation which comes to your mind naturally for the gas phase is nothing but the ideal gas equation. This is the first thing which comes to your mind, isn't it? And we know that, as we all know, that the ideal gas equation which is so very known to you, for 1 mole it is PV equals to RT. We find that this is applicable only for this, all of you know, this is applicable for very low, not even low, very low pressure and high temperature, and therefore, this particular quantity Z, which is known as the compressibility factor, this which is nothing but PV by RT, this is equal to 1 for ideal gases, and this is not equal to 1 for real gases. This you already know, and I have just depicted this in the figures here where we show that Z is not equal to 1 for any particular real gas, and as the temperature keeps on decreasing, the deviation from ideality increases. It is also a function of the nature of the gas. So, naturally, since the ideal gas equation does not suffice, what is the next thing? We would like to go for the different equations which would be predicting the PVT behavior of the gases. Now, what are the different equations that we have? The equations can broadly be classified in two ways. The first one is known as the PVT behavior of the gases, and so therefore, they can be broadly classified in two ways. One is the cubic equation of state. The immediate example of this, all of you are aware of, is the virial equation, is the van der Waals equation, and the other one is the virial equation of state. When we are not sure whether the gas obeys any particular cubic equation or the virial equation, we often refer to the compressibility factor chart, which we will be discussing after we finish discussing these particular equations of states. Now, why is the cubic equations known as cubic equations, or in other words, to be more specific, what is the speciality of cubic equations? Now, the general form of cubic equations, do not get confused, these are the whole lot of equations that have been proposed by different researchers, the general forms being this, but we are not going to deal with the host of these equations. For your purpose, be comfortable with primarily van der Waals equation, which you already know, and this equation is already known to you, the functional form is already known to you, and then there are two other equations which we will be using for conditions where the van der Waals equation fails. Right. Now, the functional form, if you observe, you find for all of this, what is the functional form? There are usually two constant equations where the constants are denoted by small a and small b for van der Waals, capital A, capital B for Redlich-Kwong, and alpha and beta for Peng-Robinson. We find that the volume correction term is the same for all of them. It is only with the intermolecular interactions which is represented by more and more complex equation in the different equation states. Now, let us see under what conditions each particular equation is applicable. This will be evident if we observe, if we observe, say, the experimental pressure versus density data for ethane. Okay. Here, what do you observe? If you observe, see this particular line, it is the solid line, it is the experimental curve which has been observed. Just note the van der Waals equation of state. We find that beyond 200 atmospheres, it fails completely. And under this particular circumstance, we find, more or less both the Redlich-Kwong as well as the Peng-Robinson equation of state, both of them are applicable for this particular conditions. Okay, and both of them are quantitative, and if you observe closely, you will find that the Redlich-Kwong equation, it appears to be slightly better as compared to the Peng-Robinson equation of state. Just to verify this, I have given you one particular problem for calculating the molar volume of ethane. This is also for ethane at 300 Kelvin, 200 atmospheres. Please do it with three particular equations of states and compare the answers that you get and compare the values with the experimental values, from where you will be in a position to understand that Redlich-Kwong equation is definitely better than van der Waals equation at higher pressures. The other thing which I would want you to do is that, suppose there is also another thing, let me explain before I go for this particular equation of state. Now, what is the speciality of cubic equations of state? The first speciality is, if you write it down in the form of the volume, then what do you get? Then for all the equations, you get a type where you find that it is cubic in volume. Now, when it is cubic in volume, it should give you three roots. Now, usually what do we find? We find that if you are working at conditions greater than T, greater than Tc, P greater than Pc, for this particular case, you will find that there is just one physically realizable root. I should write it down as one physically realizable root. The other roots are complex. Just to give you a feel, I have already given you 2 problems, do those 2 problems and you can take a few other problems. You will find that when you are operating at conditions much higher than the critical conditions, then under those conditions you get one physically realizable root. Now, when you are working for conditions where T is less than Tc, for that particular condition what do you get? That means, what I mean to say, you are working in this particular zone. In this particular zone here, this particular zone here, you find that under this condition you get 3 roots, right. One root, the lower root, it corresponds to the liquid volume, the other root corresponds to the vapor volume, and there will be an intermediate root which is the spurious root. Why? Because suppose you are trying to predict the behavior of the PV behavior using any equation of state. It can be van der Waals, it can be Peng-Robinson, it can be Redlich-Kwong equation of state. You will find none of the equation of states can predict this discontinuity in behavior. What they do? They predict a continuous curve. What is the continuous curve? The curve is something of this sort. This is what they predict, right. Now, we find that suppose for T less than Tc and P equals to the saturated pressure, which corresponds to this particular pressure, under that condition if we work, then we get one particular physically realizable root. What is a physically realizable root? It has to be positive, it has to be real, and very important, which it is not very evident, it has to be greater than B, right. It has to, the total volume of the gas has to be greater than the volume occupied by the molecules, fine. So, therefore, you will get 3 physically realizable root if you are working within this liquid vapor dome. You will get 1 physically realizable root when you are working in this particular domain. So, there, and then we find that the isotherm or the isobar is predicted in this particular way, where we find that the smaller volume, it corresponds to the liquid volume, this corresponds to VL, the larger volume corresponds to VV. Now, this particular region, what does this correspond to? This particular region, it corresponds to subcooled vapor, which is a metastable state. What does this particular region correspond to? This corresponds to a superheated liquid, which is again a metastable state, right. So, therefore, this region, and if you find this region, these 2 regions, they are metastable states. They can be obtained under very special conditions. And if you observe this particular portion, you find that for this particular portion, del P del V at constant T is greater than 0, the slope is positive, which cannot happen. So, naturally, this particular region, it is a spurious region. This region cannot exist, as a result of which the intermediate root which you get has got no meaning. So, therefore, from here what do we conclude? We conclude 2 things. The strength of cubic equations of state is that they can not only predict the volume or the behavior in the vapor phase, they can also do so for the condensed phase and more importantly for the liquid vapor coexistence region. So, therefore, we can predict the molar volumes for liquid state, vapor state and the liquid vapor coexistence curve. And just to show you one particular example, I have given you one particular problem here, not this problem, sorry, this particular problem where I have the liquid argon, and the argon exists in the 2 phases under this particular condition, and the experimental density, molar density of liquid argon and vapor argon are provided here. I would like you to verify this using the van der Waals, Redlich-Kwong and the Peng-Robinson equation of state. Remember, for all of this you are going to get 3 roots for the vapor, for the volume, and the 3 roots, as I have mentioned, they correspond to 3 points joining the horizontal line, such that the area under and the area above the horizontal line are equal. So, from each of these you will get 3 roots, out of which the higher root will correspond to the vapor volume, the lower root will correspond to the liquid volume, and we find, if you compare in this particular case, you are supposed to work out this problem. If you compare, you find that the answer for the Peng-Robinson equation of state is this. Sorry, the answer for the Peng-Robinson equation of state, if you compare the different equations of state, then what do you get? You get that the Peng-Robinson, you get that for the Peng-Robinson equation of state, whatever you have got, these particular values, they are closest to the experimental values. Redlich-Kwong equation of state, they are slightly further off, and van der Waals equation of state completely fails. This is what I have tried to show in this particular curve. Van der Waals equation could not be plotted because it was out of the range. If you observe here, this is the Redlich-Kwong curve, this is the vapor liquid coexistence portion, the Redlich-Kwong curve, this is the Peng-Robinson curve. It shows that the Peng-Robinson is slightly better than the Redlich-Kwong equation in the liquid vapor region. So, therefore, among the different equations that I have suggested, for the different equations, what do we find? We find usually that the Peng-Robinson equation of state, it is better for the liquid vapor coexistence curve. The Redlich-Kwong equation of state is better for the for higher pressures, higher pressure conditions. You are requested to work out examples and see it for yourself, and the strength of cubic equation of state is that it can predict the saturated volumes along with the vapor volumes. The weakness is that it fails to predict the condition in the liquid vapor dome. The situation I have shown here, and I have also compared it with the experimental situation. Right. Here you get three physically realizable routes. Out of these, two are meaningful, and in this particular case you get just one physically realizable routes. Now, the other thing which I would like to mention about the cubic equation of state is, as you have already observed in the cubic equations of states, what do we see? All of them comprise of some constants, right. Now, these constants are completely empirical constants. Now, each particular gas is going to have the different constants. It is very difficult to rather to find out or to accumulate, or rather to collect the different constants for the different gases. Fine. So, what people usually try to do is, they try to express the constants of the cubic equations. Say for instance, for van der Waals it is A, B, for Redlich-Kwong capital A, capital B. These things are there, people try to express them in terms of the critical constants. Why? Critical constants are much easily measurable, as we have said. They are much more constants as compared to other particular physical properties of pure substances. So, in the next class, or rather I will just be discussing very briefly, this is left as an exercise for you in order to express the empirical constants in terms of the critical constants, and then once we do it, we find that from the cubic equations of state, we arrive to a very interesting equation of state, which is known as a generalized equation, which leads us to some more interesting results. Thank you very much.